Then I just talk about for population geneticists or evolutionary biologists, one thing we usually do, it's a common practice for us, is to test whether our survey fits Hardy-Weinberg equilibrium. So you usually, this is the MM blood type example, you usually have the survey result, you know how many individuals carry one particular genotype. So here you have 3 genotypes, you have 3 numbers. So total survey is 200. Then you have, say, 114 individuals. They are MM homozygous. Then you have 76 individuals are heterozygous. Then the rest 10 individuals are NN homozygous. So that's your result from the population. And based on the population result, you can calculate frequency of M and frequency of N, right? So you can calculate how many M alleles in the population and how many N alleles in the population. And based on Hardy-Weinberg equilibrium, you know you can calculate the expectation. That's the P squared, 2PQ, and Q squared. And the expected proportion listed in the parentheses here, then that's the expected frequency of each genotype based on P squared, 2PQ, and Q squared. Then you can use this proportion times the total number of individuals in the survey, which is 200, get the expected numbers. And the numbers shown here are the expected numbers in the population if it's at Hardy-Weinberg equilibrium. Then the test is performed comparing the observed number and the expected number. A lot of us like to calculate frequency. Then we suddenly forget we have to use the number to do the statistical test. Then we use the frequency, and the frequency is always very small. So after that, the chi-square become very, very small. So it's like you never can get like significant differences. But just remember, you have to keep in mind when we do test here, we use observed number and expected number to do the chi-square test. And the chi-square test, you probably learned it from your statistics, is a comparison between these two numbers. And you have, like, so you look at the differences between the two numbers and take a square root and divide it by expected numbers. Okay, so everything is in number. Then that's the chi-square. And this is sort of like a relative simple. Then you ask whether, given the degree of freedom, whether this chi-square number is significant, or actually we're asking whether the observation is significantly different from our expectation. So that's what we are asking. If they are similar, there's no statistical differences, we'll conclude, or tentatively conclude, the population is at Hardy-Weinberg equilibrium. So all this calculation was based on the table and try to, then one thing you have to remember is we always use the numbers to do the test. And in a lot of analysis, we are asking whether natural selection is one of the important forces operating at the sequence level. In the middle of this semester, we're going to have a 2-hour lecture to cover how evolutionary biologists to test the neutrality or test whether a sequence has influenced by natural selection. Okay, just to remind you, what do we mean by natural selection? The natural selection we're concerned about is the differences in reproductive success among individuals of the same in the same population. So usually we are population-based, and we are concerning different genotypes in the population. So when we talk about individuals, actually here in population genetics, we're talking about different genotypes carried by this individual. So we will ask whether the A1 homozygous produce more offsprings compared to the other genotypes. So that's the comparison we are dealing with. We're not talking about like this particular individual to the rest of the population. We're concerning about the genotypes in the population. So if there are 3 genotypes, we ask whether there's differences in their reproductive success. Of course, that includes their survival rate because they have to survive to the adulthood to produce the next generation. And we use the fitness to describe this or to sort of measure this quantity. So the fitness, we use omega as the symbol to describe individuals' ability to reproduce. So when we talk about a fitness of one individual, if this individual produces 1 offspring, and we simply count it as 1. But that doesn't really mean anything because you don't know the reproductive success for the rest of the individuals in the same population. And also, you don't know whether this fitness is correlated with the genotype. It means this particular genotype always produce certain amount of offspring. In population genetics, we specifically focus on the genotypes and the relative fitness. So if this individual produces 2 offsprings and that individual produces 1, so the relatively this one is twice of the fitness of the other one. And we're concerning about the genotypes, we want to compare the fitness among the 3 different genotypes. So this is what we are comparing. So it's a relative fitness within the population. Okay, so back to the Hardy-Weinberg equation. Then now we want to introduce the fitness into this model. So on the top is the same thing. You have 3 different genotypes and the proportion, the ideal Hardy-Weinberg proportion for each genotype. But now we introduce the omega here as their relative fitness. Just use their genotype. So we have omega 1,1, omega 1,2, and omega 2,2 for each genotype. Then we want to look at or calculate the frequency after selection. So when I say after selection is we consider their fitness, then we just times their frequency, multiply their frequency with their fitness. So the first one, A1 will become P squared times omega 1,1. So that's their fitness. And you can do that for A1, A2 heterozygous and A2, A2 homozygous. But one thing you have to keep in mind now is now the frequency, the sum of the 3 frequencies added together not equal to 1. So you have to recalculate the frequency, the proportion of each genotype in the population. And the rule is very simple. You divide it to the sum. So the sum is plus the 3 items together. You multiply, you add the 3 items together. That's the sum of the total proportion. It's in here. Then you put the top one, and now we want to calculate the frequency of, let me see, frequency of A2 in the population for next generation or after selection. So we put QT plus 1. So that's another notation we use. So we use multiple different notations, but it's usually very similar. So if right now it's time T, then after selection is the time T plus 1. Or some people use like a Q for next generation will be Q prime. P for next generation will P prime. So that's the notation we use. So here will be, we are calculating the frequency of A2 after the selection. So that's QT plus 1. Then we added half of the A1, A2 plus the proportion of A2, A2 after selection. Then we calculate, then divide it to the sum of all the proportions, and that's the next generation Q. And this is just a calculation to sort of like simplify, but doesn't really, you don't really look this simple. So here is just, so this part is the sum of the total proportions, but up here, that's the frequency P times Q, but later part is sort of easy to remember. The P frequency of A1, initial frequency of A1, that's P, times the differences of the homozygous A1 and the heterozygous fitness. So that's the first parenthesis here. So the differences in their relative fitness. And the second parenthesis is the differences between the A2 homozygous and the A1, A2 heterozygous. So although the formula looks complicated, but the two frequency times the differences between the homozygous one and heterozygous one. So that's the explanation for this calculation. And that's the differences of Q. So in population genetics, we are not only asked what's the frequency of next generation, we are also interested in the differences between generation. So the changes over generation. So that's the delta Q showing here. Okay. So this is just to replace all the P and Q with numbers. So the numbers looks like more familiar to you than like the P and Qs. So the simplified, it's not really simplified, but that's just like the real calculation. If you know the relative frequency, then you just time the frequency to the relative fitness, and that's the same calculation. And I substitute the QT plus 1 to Q prime, just to let you know, some people use Q prime as the next generation frequency. So you have different notations, but usually it's quite similar. Here is to show you, like, because we use omega 1, 1, 1, 2, and 2, 2 as the relative sequence, but sometimes we also use standardized method. So we usually take the highest fitness, or just take the first genotype, depends on how people do it, and then use that as the fitness 1. So the relative fitness 1, and the other two, well, like a plus S plus T, or some textbooks say minus S minus T, but S and T could be any number. Then you can do the same thing, the same calculation to get the next generation frequency. Another thing I want to emphasize here, although I think I already say that, at equilibrium. So we usually after the calculation we'll say, okay, when the population will reach equilibrium. When we say reach equilibrium, or what will be the allele frequency at equilibrium. So now you look at generation to generation, there are changes through the generation. But we want to ask when the population won't change. So that's what we mean by at equilibrium. So when we say at equilibrium, that means when delta Q equals to 0. Means Q and the Q plus 1 or QT plus 1 or Q and Q prime are exactly the same. Delta Q equal to 0. If you want to do that calculation, that's the, you already know the item up there will equal to 0. Then you can calculate the frequency of, in this case, A2. Q is equal to S divided 2S minus T. You don't have to remember this, but one thing is important is in this equation, you don't see P or Q exist. The only thing exists is the differences in their fitness. So if the evolution of a gene is operating by selection, then this is the equilibrium frequency of the one of the allele, and you can calculate purely based on their relative fitness. So that's the important part. So no P or Q, no initial P or Q involved in this formula.